Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step one aside as we jump into section 6.2 in the Big Ideas Math Integrated Math 1 textbook. We are doing exponential growth and decay and their models with equations. Now, it's interesting because in the last section, which by the way was a doozy of a section, wasn't it? A lot of the graphing exponential functions. Probably not doing that here. I don't know for sure. But in the last section, we had one or two problems that reminded me of this kind of question. At least there was one open-ended one where I made it like that, only because it came after on the heels of one that was kind of like it. I forget which problem was specifically, but it had to do with percentage increases and decreases of things. So we're going to dive into this a whole bunch more. You will need your calculator for this one. Doesn't need to be a graphing calculator as far as I'm concerned, but you'll need your calculator for this one if you want to follow along properly, and we're going to work off those formulas. So I'm going to begin with the lecture portion, and if you'd like to jump to the description section down below, you can find the PDF for this entire thing. Note this PDF is slightly larger in file size. There's an image on the first page that for some reason makes it like 5 megabytes larger, so I hope that's okay. But if you'd like to not download that page, that's cool as well. And you could also find the timestamps for the problem set as I begin with the, like I said, the lecture portion. Then I'll begin with the 58 question problem set. I feel like I'm syncing. Yes, I am. Okay, so that happens every so often. Without further ado, I'm going to go ahead and get started. We're going to use and identify exponential growth and decay functions and solve real-life problems involving exponential growth and decay. This is, I think, the bigger portion, whoopsie, of what we do here. It's mostly word problems, I believe, to do things, money and things like that. I think there are going to be a lot of things with this involved, but identify growth and decay functions is determining whether or not, or whether it's growth or whether it's decay. In the last section, we did whether it was an exponential function. I think this time they always will be, and then we have to do more off of it. So a lot of phrases right here, the exponential growth function, exponential decay, and decay function. Now, I stated growth and decay quite often in the last section when we talked about the graphs. This was an example of decay, whereas this was an example of growth. There's also this phrase on compound interest, which I didn't know this was going to pop up in IM1, but there it is, compound interest. We'll talk about that when we hit it. Exponential growth occurs when the quantity increases by the same factor over equal intervals of time. Now, when you saw the equation y equals ab to the x in the last section, b was the growth/decay factor. If b was greater than 1, it was growth. Because if you multiply by a number more than 1, the number gets bigger. I mean, bigger positive, bigger negative, what have you, it got bigger. My guess is when we hit word problems like these, the A value will most always, if not always, be positive because we're talking about things in real world scenarios, often population and money, and those two things tend to be positive, according to my records. And so we're going to talk about, they don't mention positive versus negative, growth versus decay, but when I say growth, we're talking about the numbers getting bigger, basically. Now, we have the formula that looks slightly different here. Instead of b, it has 1 plus r, and instead of x, it has t. Does that change the nature of what's going on? No, it's still an exponential function. T is now the new variable, if you will, where y is a function of time, of something over some amount of time when something occurs. So this is like your new x, of course, and b is like your 1 plus r, because this plus represents growth of some r, some rate. Now it says decimal form of that rate, given that it first exists as a percentage. So if we're talking about 50%, that decimal equivalent is 0.5, things like that. And that's what we're going to convert it to. Now the 1 has to do with being 100% of something. We either add to 100% of something or take away from 100% of something to indicate that percentage growth or decay. How much added to, how much taken away from. And when we multiply that by it, and I think, in fact, that's now ringing a bell as to which problem it was. It was something where visitors were going to like a museum or something like that in the last section. And it was like a 6% increase. So a 6% increase, we'd multiply by 1.06 so that the numbers kept getting bigger. That represented a 6% increase over time. So this is the same thing as that, just a different representation of it. It's still an exponential function. Okay, A is the initial amount. If you thought of it before as the y-intercept, is the value of y when t equals 0, when you have 0 time, so the initial. Oh, they just state note here, b is replaced by 1 plus r and x is replaced by t. Perfect. Okay, here's that image I was talking about. This thing loads pretty heavily on there. I hope that's okay. Okay, the inaugural attendance of an annual music festival is 150,000. The attendance y increases by 8% each year. So they say write an exponential growth function that represents the attendance after t years. Notice that there's a model question in place here before they go to part B and they substitute something for t. So we actually have t in our answer that we do here, and we will simplify what happens. So A is the initial, it's not population, but the initial attendance, the initial amount of people. And then 8% is converted to 0.08 in its decimal form. So we do 1 plus 0.08, and then we simplify that, of course, that turns into 1.08. Now this looks like a y equals a b to the x power. I mean, x is t, but this now becomes your b value. B being more than 1 means this will be exponential growth, kind of as expected. The attendance increases 8% each year. That's part A. This is your model for this thing. That's the growth function. Part B, how many people will attend the festival in the 5th year? Round your answer to the nearest 1,000. Not thousandth, not 3 decimal places, but so that way there are only zeros, like a 960,000, things like that. So let's see what they get here. The festival attendance can be represented. Oh, there it is. Okay, so the value t equals 4 represents the 5th year because t equals 0 represents the 1st year. That's a little tricky. That's a tricky portion of this question, and we have to have discussions on those each time, depending on what the question is stating for us. It did say the inaugural attendance is here, so the 5th year, oh, that is tricky. We'd have to talk about whether that would be that or not. Okay, so that's the 1st year. That's the 1st year, it's not the 0th year. Interesting. So we're going to substitute 4 for t in this situation. And then here we get approximately this. Note that we're going to use our calculator for this part, literally straight up. If I go to the calculator, I would type 150. Let's reset it. It's already crashed. 150,000 times 1.08 to the 4th power. Let your calculator do all the order operations, all of the, don't round early, nothing like that. And this is the number that we get. Decimals and all, that's the number that we get. Now, they don't want you to round to the nearest person. They want you to round to the nearest 1,000 of people. So 204,073 people, round that down to just 204,000. About 204,000 people will attend the festival in the 5th year. Now, I think it's important for me to start mentioning that although we'll talk about different forms of population, there could be people, there could be deer, fish, bacteria, what have you. Normally, you're rounding to the nearest whole amount. You wouldn't have a decimal amount. If they have you do any sort of rounding like this as requested, we'll do that as well. If we deal with money, and we will, we'll see if they want us to round to the nearest $1,000 or the nearest dollar or the nearest cent, which means 2 decimal places can be applied. So we'll make sure to hit those. As you can tell, these are already real-life application problems. Okay, we just saw exponential growth. Let's also look at exponential decay. Now, the formula is going to be the same kind of thing, but when it comes to decay, b becomes not a negative number, but a number between 0 and 1, right? A fraction, if you will. But we're going to write it as a decimal because we're talking about a percentage adding to or taking away, at least for the most part. But, when we did equations in the last section, like 6 times 1/3 to the x power, 1/3 is between 0 and 1. So when you multiply by 1/3, your numbers get smaller. That makes it decay. Now this will look a little different. So what happens a little differently in this formula? Instead of 1 plus r to the t power, it becomes 1 minus r to the t power. That doesn't make this become a negative number. R is generally a percentage that's less than 100%. So if it's like 64%, you're doing 1 minus 0.64. That's still a positive number. It's just a decimal less than 1. But the same situation happens. It does become decay. That way, as time goes on, you are losing certain amounts. If I said 64% decrease, you're losing 64% every time you multiply by that simplified version of this number. And please do simplify the numbers. Okay, it doesn't look like they have an example straight up there, so we will obviously hit our own. But for exponential growth, the value inside the parentheses is greater than 1 for growth, is greater than 1, because r is added to 1, whereas for decay, it's less than 1, because r is subtracted from 1. So there's one versus the other. We want to identify growth versus decay on these. Now, note, these will all be exponential functions. The question is, are they growth or decay? So part A is going to be exponential decay. We're going smaller on y as x increases. And that's really the only thing that you need to be able to answer on that. But if they ask you to come up with, and we can as well, what you're multiplying by to go from one number to the next, you can also determine that. I stated this in the previous section, but you may say this is dividing by 3, but we never say what we're dividing by. We say what we're multiplying by. These formulas are based off multiplication of something over and over. That's what exponents literally are. So instead of saying dividing by 3, we say multiplying by 1/3. Now remember, if you have trouble with figuring out what this number is, divide a number by the one before it. 90 over 270 is reduced to 1/3. 30 over 90 is reduced to 1/3, and 10 over 30 is reduced to 1/3. It only takes one of them to figure it out because we know it's exponential. So pick the one that's easiest for you. Anyway, that's exponential decay. 1/3 is less than 1. This is exponential growth. As x increases, so does y, and it is, of course, exponential. We're multiplying by 2 each time. 2 being greater than 1 represents exponential growth. Easy peasy on those ones. If they ask us to figure, well, I will represent what those numbers are, what you're multiplying by each time, because there's more to these numbers that we might have to represent, such as what percentage change is it? We'll see if that shows up. Interpreting exponential functions. Determine whether each function represents growth or decay, this time by the equation, not the table. Identify the percent rate of change. Okay, so this is perfect. Back to what I was just talking about. This time we have the decimal, though, which makes it easier. Y equals 5 times 1.07 to the t power. Keep in mind, by order of operations, guys, you will not multiply these two numbers before raising to the t. We do this first, and then we take care of the times 5. That being said, our formula has one of two appearances. There's 1 plus r to the t power, or 1 minus r to the t power, which actually shows up down here. When you'll use the 1 plus r when your number is greater than 1. 1.07 is greater than 1, so 1 plus r being 1.07 means r is 0.07. That's a 7% growth. That's what makes that so. You can think about it really that other way. What r would I need to have so that when I use it in the formula, I get 1.07, right? We're subtracting 1 from it to figure that out. That's the algebraic portion of it. This is exponential growth of 7%. The next one, f of t equals, we have an initial amount of whatever. It actually doesn't matter. This part here, the 0.98 though, that's a number less than 1. How much less than 1? Well, we're doing a 1 minus r to figure that out. If 1 minus r is 0.98, I generally do the add r over and subtract 0.98 over, and you get 0.02, which represents 2%. Remember, 0.2, we haven't seen that quite yet, but 0.2 would be 20%, whereas 0.02 is 2%. Okay, anyway, that's exponential decay in that case. You lose that amount. That's the rate of decay. Solving real-life problems. Well, it felt like those ones were real-life problems, but let's see what they want to talk about here now. Exponential growth functions are used in real-life situations involving compound interest. Okay, the last ones are maybe models, and they're right. These ones are things that literally happen, like in a bank or whatever. Although interest earned is expressed as an annual rate, the interest is usually compounded more frequently than once per year. So the formula must be modified for compound interest problems. Okay, so a couple things here. First of all, when dealing with interest, you are dealing with an increase every time. So the plus that you see here in this formula, or in this formula here, will always be that. An interest is increased. That sounds easy to remember. They start with in. Second of all, t has been a time that before could have been represented as anything. It could have been a weekly percentage increase or decrease, a monthly one, a daily one, an hourly one. It could have been a yearly one, or a decades-long one. In interest formulas, t is always represented as years, number of years. They have to say that somewhere. Here it is. T is time in years. If you notice in the previous formulas, they did not say, they probably just said t equals time. T equals time. So here, they will express for you what that percentage growth or decay is on what timely rate they have. If they say a monthly increase of 5%, then that's in months. But this is always in years. This is important to state because they might not always measure things in years. They might measure something in months, and we have to do a conversion of our years to months or whatever it is. I'm sorry, I kind of have like a hiccup thing going on here for right now. Anyway, so that's the two things I wanted to mention with regard to interest. Now, compound interest is a whole different animal because what happens is you divvy up your percentage a certain amount of times throughout the year so that you can in turn compound it and use it that many times in the year. You can compound annually, which then n would just be 1. Notice if n is 1 in this formula, then it becomes what it was before. 1 plus r to the t power, because r over 1 is r, and 1 times t is t. So that doesn't change this. By the way, notice that the p turned into an a, or the a turned into a p. That doesn't matter. It's still your initial amount. They call it principal amount. Sometimes I see this as an a. If you ever see me write that as an a, that's fine. That means accrued amount, how much you earn over that time. The balance of earning that much. Anyway, so annually, n would equal 1. Semi-annually, n would equal 2. Quarterly, n would equal 4. Monthly, n would equal 12. The point is, n, like 12, would go in right here and right here. So you divvy up the R value 12 times throughout the year just so you can compound it 12 times in the year. Now that gets you a slight bump in dollar amount, not very much. It gets you a slight bump in increase, and banks sometimes offer those options. Okay, so writing a function. You deposit $100 in a savings account that earns 6% annual interest compounded monthly. So 100% or $100 is your principal amount. 6% annual interest, that's your R value, but of course we need the decimal equivalent. Compounded monthly, this is where you get an N value of 12. P is 100, R is 0.06, N is 12. Write a function that represents this. So they do a few things here. They do substitution of, they do simplification of the inside. 0.06 over 12 is 0.005. 1 plus 0.005 is 1.005. And they turn it into this. So it's one version of it. It's still to the T power. They didn't even ask us to represent it at all. I don't know if they're going to say that right here. Nope. So that's it. They just said write the function like that. That's it. If they said find it after 20 years, great. You can substitute 20. Okay. Another example, let's see if we actually use it this time. You have a checking account and a money market account at a local bank. Your checking account has a constant balance of $200. The table shows the total balance of the accounts over time. Your checking account has a constant balance of $200. Okay. Write a function M that represents the balance of your money market account after T years. So I'm trying to figure out where the 200 came from. I totally missed that. I'll take a look. Oh, my checking account. Okay, my checking account doesn't grow. It just stays at 200. I thought it was a part of this model. I'm like, what are they talking about? Now I hear it. Checking account and a money market account. Okay. So the money market account will be M, right? So we're going to use they use M of T, so it's just replacing Y. So your money market account here, that's a function notation. Now this thing is just an annual. Where does it say this? This is just an annual change here from year 0, 1, 2, 3, 4, etc. But what we have to do is come up with the percentage growth change, right? How much it's increasing by. To figure out how much it's increasing by, we're going to have to do some sort of, I don't know, division. Let's see if they say. Because I would be doing a division of one number versus the other. Oh, this is different. This is my total balance. Here we go. Here's the money market account. The total balance adds 200 to these numbers. Perfect. Got it. Okay, sorry. I look at these the first time as you do. Anyway, we go from $100 to $110, then $121, $133, etc. What I need to just make mention of right now, as you see this in a table, guys, is notice this is not a constant increase. We're not just adding $10 every year. We added $10, then $11. Does that mean the next year's $12? No, actually the next year is $12.10, and then $13.31, and then $14.64, right? It keeps changing a little more over time. Why? Because that's what exponential functions do, and that's the point of it. You're getting a certain increase of the previous number over that time. That's why it grows like this. That's the cool part about it. It's not linear. It's going to grow over time. So from year 19 to year 20, it's not just a $10 increase. It might be a $100 increase. It's going to be significantly more based on what you have. So anyway, from the table, it says the initial balance is 100 and increase 10% each year. How do we know it increases 10% each year? Because you can divide one number by the one before it. If we look at from year 0 to year 1, we have $100 to $110. So if we divide one by the one before it, we get 1.1. Now, as far as our formula goes, 1 plus R is 1.1. When you subtract 1 from both sides, R is 0.1, and 0.1 represents 10%. Because it's a plus, it represents an increase. This is an interest amount. So there's a lot that's not stated in how they got the 10%. That's what I've been fishing for this whole time. There's a lot that's not stated in how they got the 10%, and that's where it comes from. That being said, we get back to this formula again, so I don't know if it's important for us to kind of make mention of what the increase is, as long as we can come up with the number itself. But I'll be making sure to mention both. So that's the M of T equation. Write a function B that represents the total balance after T years. Compare the graph of M to the graph of B. So the total balance after T years is going to add the $200 constant amount. That's why this is $200 more than 100, $200 more than 110, things like that. You're just adding 200 to all these numbers, which makes it a constant added to it. It's like a plus K, if you will. In fact, here are the two graphs. This is just a vertical translation. It's 200 units upward from the previous one. That's what they're saying. It's a vertical translation. Part C, now I don't know if we're supposed to graph, but Oh yeah, compare the graph of M to the graph of B. So maybe we'll use the graphing calculator on those ones and just take a look and state that. Maybe not drawing our own graphs. Part C says compare the money market account to the savings account in example 4. Oh, so we get to use this example 4 for this one. This is $100 that earns 6% annual interest, but it's compounded monthly. This one's just compounded annually, so it uses 10%. It's a larger percentage, but it's only compounded once per year instead of 12 times per year. So when it says compare them, we'd have to come up with, well, they don't really state this part. They say each account has an initial balance of $100. This one earns 10%, whereas this one earns 6%, so the balance of the money market increases faster. They're not wrong. They're not wrong, but we do have to take into account that if all things were equal, including interest rates, that if you compound more, you will earn more, you'll yield more interest as a result of that. So 6% is significantly less than 10%. It's almost half the amount in comparison. So compounding monthly will not make up the difference. But if it was 9.9% versus 10%, I mean, compounding monthly is probably going to make that difference. So that's an interesting comparison when they state that because they didn't talk about the compounding effect. Okay, is that the end of the lecture portion? Let's see. That's the end of the lecture portion, guys. We have 1 through 4 in vocabulary and core concept check to begin with. After that, we have numbers 5 through 58 to do, which could go quickly. It all depends on what we're doing there, especially now that we talked about the sets. All right, number 1. Complete the sentence. In the exponential growth function, y equals a times 1 plus r to the t power, the quantity r is called the, I'm going to call it the interest rate. Wait, the rate. Rate of growth. They are being very specific about separating the 1 plus r formula from the 1 minus r formula. If you ever see me write this, which I likely will, I'll write 1 plus or minus r, meaning this can work both one way or the other. Exponential growth is plus, exponential decay is minus. So when they said 1 plus, that'll specifically be in a growth rate in this case, because r is never negative. You can only add or subtract it. What is the decay factor in the exponential decay function y equals a times 1 minus r to the t power? The decay factor is the 1 minus r. The 1 minus r is representing what we multiply by each time for that number to go down, and it will go down because that number will be less than 1 because we are subtracting r in that case. It's not just r. Compare exponential growth and exponential decay. Well, exponential growth, let's see. They are both percentage increase, percentage changes from 100%. However, growth is an addition to 100%, and decay is a subtraction from 100%. And they're obviously both exponential and all that kind of stuff, but just as far as the formulas go, one is a plus, one is a minus, and those are the changes that we seek when we are making the equations. But they're both added to 100% and subtracted, right? We use the number 1 to represent 100% because we're in decimal form. But that's how I'm seeing those two comparisons. Number 4, so growth increases over time, decay decreases over time. Number 4, writing, when is the function y equals ab to the x represent exponential growth and exponential decay? That's one of the things I was bringing up earlier in the lecture portion. Exponential growth is when b is greater than 1, and exponential decay is when b is between 0 and 1. Now, we're often not going to see these as fractions in this section because we're going to talk about percentages and convert them to decimals. So a number more than 1, we could see 1.82, 1.01. You could see 2 point something. That would be a massive increase. These, you'd see something like 0.34, 0.01, 0.96, things like that. All right, guys, we're going to get started on the problem set itself. So again, get your graphing calculator ready in case we have to do a lot of calculations here. Your calculator, I should say. Otherwise, I'm going to go ahead and get started on my own. In exercises 5 through 12, we're going to identify the initial amount a and the rate of growth r as a percent of the exponential function. Evaluate the function when t equals 5. Round your answer to the nearest tenth. So on number 5, we have y equals 350 times, they have them separated to begin with, 1 plus 0.75 to the t power. This stems literally off of the formula that looks like 1 plus r to the t power right here. Now, they said identify the initial amount. The initial amount is a. We don't know what units they are, so I'll just say a is here. The r value, they said, represent it as a percent. 0.75 is 75%. That's a decimal shift 2 places to the right, or you can multiply by 100. So there's that. Now they said evaluate when t equals 5. So we're going to do y equals 350 times, and look, I'd love to simplify this, write it as 1.75, and raise it to the 5th power. This is where the calculator comes into play, and I'm going to be flashing it for the first couple. After that, I'm probably going to leave it. This was from the lecture portion earlier. So 350 times 1.75 to the 5th power. Let your calculator handle all of that for you. And we get 5,744.58. They said round to the nearest tenth, so we'll do 0.6. 5744.6. Oh, that was one problem. That actually took a little bit longer than I expected. All right, number 6. Also a growth. In fact, these ones are all growth to begin with. They probably do decay after. But number 6, we have y equals 10 times 1 plus 0.4 to the t power. Now the a value is the initial amount that's multiplying out in front right there. So the a value is 10 somethings. Now the r value, be very careful. This is not 4%. It's actually 40%. There's a trailing 0 that's just not seen. So 2 decimal places over, or times 100. That's why I state that. Do one or the other. Don't make a mistake. It is 40% in this case. Now when we substitute 5 this time, now 1 plus 4 is 1.4. So 1.4 to the 5th power. I'm going to do this off screen. It takes longer to do switching than it is to actually calculate. That's, unless I typed something wrong. Is that right? Oh, I typed something wrong. I typed 0.4 instead of 1.4. That is just perfect. All right, 1.4 to the 5th power. I'm getting, because I got a decay, 53.7824. So around 53.8. 53.8. Number 7. Y equals 25 times 1.2 to the t power. This time, well, the a is, as you can see there, the a is going to be 25. The r might take a little more work depending on what you're doing here. Remember, the formula is 1 plus r to the t. So in this case, our 1 plus r is 1.2. And when you subtract 1 here, you're getting r as 0.2. Now, the percentage version is 20% on that one. So just be very careful on what you're working on there. You can subtract 1 mentally. That's up to you. Hey, there's a 1 in front. Take away the 1, you idiot. Right? That kind of thing. You can just do that, but you got to write it in its percentage form as well. Now we're going back to the formula, and it is simplified, which is ideally what you want in your models when you're doing your work, just not when you're extracting information always. So 25 times 1.2 to the 5th power. I'm getting 62.208, or about 62.2. Number 8. Number 8's a lot like number 7 with regard to what we have there, so I can probably expedite this a little bit more. 12 times 1.05 to the t power. It's really hard to get the a portion wrong here. A is 12. That's your initial amount. Remember, it's like your y-intercept. Value of y when x or t equals 0. Now, r this time, see if you can recognize it. We're adding 0.05 to 1. 0.05 is also 5%. You're increasing something by 5%. That's what that appearance looks like. Now, let's increase something. Let's increase 12 by 5% 5 times. What do we get? Because that's what's actually happening here. 1.05 to the 5th power. Whoops, I hit a little negative sign on this thing. Give me 1 second. I'm getting 15.315377875, better written to the nearest tenth as 15.3. And again, these are non-contextual. We have no units to speak of here, so they say round to the nearest tenth. We'll have to take their word for it. Clean gospel. Clean gospel. F of t. Does that change something in comparison to y? No. It's still a function. 1500 times 1.074 to the t power. Now, a is 1500, whatever it represents. R as a decimal is 0.074. This time I'm going to do a movement this way, 2 decimal places over to give you the percentage. It's 7.4%. So there can be trailing numbers. That doesn't mean you can't have a decimal in your percentage itself, right? As this one clearly does. But we still have to write the percentage version of it. Now we do a 7.4% increase 5 times of 1,500. And I have no way of guessing what these are. I just know the number has to be bigger. Not significantly bigger. This is only 5 years later of a 7.4 increase. So if I get something like in the 1800s, I don't know if that's right or not, but it sounds good. If I get something in the 15,000s for this question, that sounds wrong. This is 2143.4. When rounded down. It was a 0.44 on there. Okay, number 10. Again, a lot like number 9. They kind of keep the evens and odds intact in that way. For the most part. H of t equals 175 times 1.028 to the t power. A is 175. R, if you notice from the last one how this works, shift this 2 decimal places over. Ignore the 1 because we're talking about our growth. This is 2.8% growth. 2.8% growth. They did say identify the percentage. Yeah, the rate of growth. So we don't have to say the word growth. Oh, I was writing y for a couple of these. Let me do this, even just for the last one. This was an f of t equation, right? So I'm going to say f of 5 and f of 5. Just to kind of keep within. Same with this one. H of 5. Let's use function notation there. 175 times 1.028 to the 5th power. Doesn't matter what I'm evaluating there, or doesn't matter. Doesn't change my evaluation. 200.9. I want to try and apply context to these, but until I can, it's kind of hard to make up things with it. Because most of it's, you start with $175 or 175 people or whatever, and it's increasing by a certain amount. All right, this one's a little interesting when it comes to the growth rate here. G of t, and it's still function notation, by the way. G of t is 6.72 times 2 to the t power. This could be $6.72. I don't know, but that's still the a value. That's the number that's multiplied in front there. R, keep in mind how this works. 1 plus R is 2. R is not 2 in this case. R is actually 1. 1 means 100%. If you multiply something by 2, you increase it 100%. You take whatever it had and you add another whole amount on top of it. That makes total sense from here. So if I double 6.72, right, I get, 13.44, I suppose. But you don't add more 6.72s after that. After that, you double 13.44, and then you double that, We're going to get somewhere in the 200s, I believe, for this one, if you do it 5 times. So let's do G of 5 equals 6.72 times 2 to the 5th power. If this was a normal number, this would look really familiar to you guys when it came to graphing. How we do times 2 times 2 times 2, right? So we just got to do this times 2 several times here. I don't even know if this would be approximated. Well, we're going to round to the nearest 10th still, so let's see what it turns out to be. 6.72 times 2 to the 5th power. 2 to the 5th power, by the way, is 32. Another way I can think about it. This is 215.04. 215.04, but rounded to the nearest 10th is 215.0, or 215, but that's what it is. Now, number 12 is the first interesting one when it comes to A, but if you were with me on the previous section on graphing things, you probably saw a lot of these, and it made no difference to us. P of t is 1.8 to the t power. Notice this is the number that's being raised to the power, therefore this is being multiplied by some number in front. That number must be a 1. Our a value is 1. The r value is how much you're adding to that 1. That's 0.8. That's an 80% growth. So here we go. From here, starting from 1, we're going to increase by 80% 5 times. So 1.8 to the 5th power, because you don't have to write it like that. You just got to identify what they are. 1.8 to the 5th power. Expect a lot of decimals to show up on this one. This is 18.89568, so around 18.9 when rounded. Okay, not the fastest problems, but it was very similar-esque in what we did on each problem. So hopefully we felt pretty good on that. All right, next exercise is 13 to 16. We're going to write a function that represents the situation. Notice there's nothing we're really solving here. We're just writing out what the function states. So number 13 says sales of $10,000 increased by 65% each year. Given that we just came off of growth things, I imagine these are all still growth things. We have to look at their words. They state the word increase each time. I want to state that as well. There are other words they could say other than increase. They could say, obviously, interest. They could say grow. They could say appreciate by. They could, I'm actually hard-pressed to think about all the words that they actually use here. Having trouble suddenly what they are. But they use different words, and they could all represent increase. Anyway, in this case, $10,000 is your initial amount. That's our A. Your R is 65%. That decimal equivalent is 0.65. So with our formula being, once again, y equals A times 1 plus R to the t power, we only have to do two things in this situation. Substitute and simplify. That's it. So y equals $10,000, and then you do 1 plus 0.65 to the t power. That's our substitution. Our simplification is 10,000 times 1.65 to the t. And that's it. That is it. You don't do 10,000 times 1.65. Order of operations take effect. There's the t there. There's nothing to solve because they didn't give us a certain amount of time. It's per year, but they didn't ask after 10 years what's the amount and things like that. But sales increased by that amount of time over that amount of time. Number 14. Your starting annual salary of $35,000 increases by 4% each year. That's a small salary to begin with. But A is $35,000. Increases by 4% each year. That's an R of not 0.4, but 0.04. So this equation will become y equals 35,000 times 1 plus 0.04 or to the t power, or 1. Yeah, don't forget that t. That's what makes this thing grow over time. Otherwise, you're just doing a 4% increase once, not over any number of t years. Now, with your permission on some of these guys, I can probably simplify this straight up. You just put the 1 in where the 0 is on these questions as long as it's as simple as that. So I'll probably do that for the next two. Number 15 says a population of 210,000 increases by 12.5% each year. Let's write a model for that one. It says write a function. I wonder if I should be saying f of t or something like that. I won't be, but so your initial amount here is 210,000. And your R value in this case is 0.125. Notice at 12.5%, it starts right here, move 2 decimal places over or divide by 100. That's where you get your number. Just because there are 3 numbers after the decimal doesn't make it a hundreds value, right? So anyway, this one is going to be y equals 210,000. And then, like I said, 1 plus this is just that. So straight up, you can get right into there. But do make sure that you simplify it, just like I did. And then we're all good. And then the last one, number 16, says an item. Notice they're all about money and population. An item costs $4.50. There could be more things, by the way. That's your initial. And its price increases by 3.5% each year. Sounds like the cost of a burger. Its price increases. Sounds like a Disney Plus subscription. 3.5% each year, that's 0.035. So here's your original decimal, 2 places over, boom. Or your original percentage and 2 places over, boom. Increased by that amount, we have, I can write 4.5 and be good with that, right? But 4.5 times 1.035 to the t power. All right, a little bit quicker than the first questions we had, but there we go. Modeling with mathematics. The population of a city has been increasing by 2% annually. All right, that sounds like our R value. It is an increase. Regardless, that's our R. That's 0.02. The sign shown is from the year 2000. So that is our A value. 315,000 is that. They say from the year 2000. Think of that as year 0, if you will. It says write an exponential growth function that represents the population t years after 2000. So t years after 2000, in the year 2000, that would be year 0. Right? So when we do this, we could say y equals, and the same thing as before, 315,000. It is an increase, so I can do 1.02 to the t power, like that. That is our formula. It's our model. Part B says, what will the population be in 2020? Round your answer to the nearest 1,000. 2020, that's where t will now be 20. Not 2020, just 20, because that's 20 years after the year 2000. So the y value in this case is 315,000. Times 1.02 to the 20th power. Let's explore this in the calculator. To begin with, type in exactly what's written. Spare no mathematical symbols and all that. Work that out. So we get this number here to begin with. I'm even going to approximate it here. I'm going to do 468,073 0.4297, just to really get it in there, okay? So we get this to begin with. They said round to the nearest thousand, not thousandth. These are people. So 468,000, I think, will be the buck as long as it was 500 or less than 500. We're going to do 468,000. So 468,000 people will be the population. I assume this is people. Will be the population of Brookfield in the year 2020 if this all holds up. Okay, number 18. A young channel catfish weighs about 0.1 pounds. So this is not population or money, this is weight. During the next 8 weeks, for this, which this model will apply, I suppose, its weight increases by about 23% each week. So our initial amount here will be 0.1 for this catfish. It's around, what, 1.6 ounces, I guess, then? And then during the next 8 weeks, its weight will increase by 23% each week. This is a good time to mention that, I mentioned this in the lecture portion, that a times 1 plus r to the t power, t can represent, because I think so far we've done annually, right? Every year. T can represent any time period at once, and as long as we have a percentage involved with it, we're going to use that. So when they say write a growth function that represents the catfish t weeks in the 8 week period, don't worry about the 8 right now. Don't worry about the 8. This is t weeks later. So this is y is 0.1 times, and 1 plus 0.23 is 1.23 to the t power. Notice this t is represented actually in months. It is in months. Or weeks, excuse me. It is in weeks. So I want to mention that it can change in these situations. Interest problems is always in years, and I'll make sure to remind you of that when we hit those problems. Part B says, about how much will the catfish weigh after 4 weeks? Round your answer to the nearest thousandth. So this is going to be 3 decimal places on this one. 0.1 times 1.23 says after 4 weeks. You know where I have to be careful on these things is that and in fact, I should have, the last population one said in the year 2000 and t is the number of years after 2000. So that was good. Because the lecture portion one kind of concerned me on that one when they said, hey, the inaugural attendance was the first year and this is the 5th year. It says a young channel catfish weighs about 0.1 pounds. They don't say in the first week. So during the next 8 weeks, so I do substitute 4. Sorry to confuse you there. I wanted to make sure I don't plug in 3 because the lecture portion did something a little tricky on a problem where we had to plug in 1 less because the initial amount was the first of what they were talking about. Anyway, I'm going to do this in the calculator as well. I'm getting 0.1 times 1.23 to the 4th power. And we're getting 0.228886641. So I am going to write that decimal to begin with just so we know what we're referring to here. 86641. They want to round to the nearest thousandth. Nearest thousandth. So in this case, look at these 4 decimals. If this is larger than 5 or 5 or more, then this will kick up to the next number. So this will be 0.229. So 0.229 pounds is the rounded version of le catfish, which is more than 0.1, right? It's almost about 2.5 times more than that after 4 weeks. So don't worry about the 8-week portion. That's just their model for what they're saying, how it applies. It's probably scientifically accurate. But after 8 weeks, maybe the model lessens over time. The catfish isn't just going to become like a 1,000-pound fish over time. Just like us, right? We start gaining weight. We gain weight for a while up through whatever time, and then we stop, or we keep eating or whatever. But the point is we don't go to like 1,000 pounds. We eventually just normalize out when we stop growing. All right, in exercise 19 to 26, identify the initial amount A and the rate of decay R as a percent. So this is going to be a lot like the first set. We're just going from growth to decay. Interesting on how much they distinguish this. This is just using the formula y equals A times 1 minus R to the t power. Now the first 2 questions they have, you can see the minus there clear as day. We're going to be utilizing that, but that doesn't change how we write the percentage. We don't write it as negative or anything like that. So on number 19, we have y is 575 times 1 minus 0.6 raised to the t power. Our a value, still that initial amount, doesn't change. And the r value is how much you're taking away from 1. It shows the minus. We're taking away 0.6. 0.6 is 60%. Doesn't change how we do business there. Now they did say when t equals 3, we're going to evaluate the function. This time it's not 5. So 575 times, and by the way, get used to doing this. 1 minus 0.6 is 0.4. I would definitely simplify that. And let's do to the 3rd power. So in my calculator, what you're now going to expect are numbers that get smaller than what they were before. I started with 575, and now suddenly it's going to reduce by a little bit. Quite a lot, actually, 36.8. They said round to the nearest tenth, 36.8 is exact. So y equals exactly 36.8. Number 20. Samesies. They show the subtraction as it is. So we can identify them straight up. I love the progressive system that they have on these, of course. 1 minus 0.5 to the t power in this case. The a value is 8, and the r value, is 0.15. That's 15%. There are those two parts. Let's now substitute 3 for t. So we get 8 times, and of course, I want to subtract these, show you that version. That's 0.85. If you have trouble with those, think of it as 100 minus 15. 100 minus 15 is 85, but the decimal equivalent that we need is 0.85. Now, these things have been doing percentages longer than, I'm going to do this off screen. These have been doing percentage changes longer than I've been even talking to you guys about this stuff, so I assume at some point you learned how percentage conversions work and why they are what they are, so I'm not going to spend time talking about that. This is around 4.9. It was 4.913. So I'm putting 4.9, which of course, just as confirmation, it's less than 8, right? That's what's happening there. It should be less than 8. I have no good ways of guessing all of what these are going to be close to. So if I guess, I can be way wrong. Number 21, g of t, already function notation showing up. And what else is changing? This now just says 0.75. Does that make r be 0.75? No. Do we multiply by 0.75? Yes. But what is the percentage decrease is what we're talking about. So let's talk about that and work that out. We have two ways of talking about it. One is kind of through that logic sense. If you're taking 75% of something, how far away is that from 100%? It's 25% away. Therefore, r will be 25%. Now, if you need a different version of how that works, of course, we can use the calculated version of it. 1 minus r is some 0.75. So if I add r to both sides, I'll just put r here, and subtract 0.75, 1 minus 0.75 is 0.25. And 0.25 lends itself to 25%. So you're asking, what do I subtract from 1 to get my number? That's our answer for that thing. 25% decay. Keep in mind, these are all decays, not increases, not growths. That being said, we are now substituting 3 in for t, so g of 3 equals. And I want to kind of think of this one on my own before we start. 75% is 3/4 of something. 3/4 of 240 is 180. 3/4 of that is 135. 3/4 of that is 30 something. So this is going to be around 90. Around 90 or 100 something. I'm going to say like 101. It's going to be close to 101. Okay, let's try it. 240. To the third power. 101.25. Very close. So, I probably, if you gave me a little more time, I could have come up with the exact. Now, we're rounding to the nearest tenth, so 101, 101.3. KKIQ, the best variety for 70s, 80s, and 90s. Okay. F of t, number 22. 475 times 0.5 to the t power. You know, 0.5 as a decimal, also, it doesn't mean 5%, right? It means 50%. So if you take 50% of something, how much are you taking off of that something? 50% of is also 50% off. This is a 50% decrease as much as it is you take 50%. That's half of something, right? Dividing by 2. So if we do f of 3, in this case, we're going to take half of 475, then half of that number, then half of that number. Something else I could try and do in my head. Let's see. They're all decimals. It'll be a little tricky. So I'm just going to get the roundabout. Around 230, 120. It's going to be in the 60s, I think. So let's see. 475 times 0.5 to the... You know what else I could do there is divide by 8. Because dividing by 2 3 times is also dividing by 8. To the third power, 59.375. So 59.4. When rounded. Yeah, dividing it by 8 will also do the trick for that one, right? Easier one to think about, of course. The other one's probably not so much. Like this one, I'm probably not going to do this in my head, and the number's probably not going to be too far away from 700 either. So, number 23, we have W of t equals 700 times 0.995 to the t power. So, A is 700. Let's go more in a conventional way here. If 1 minus R is 0.995, then 1 minus 0.995 is R, right? That's what we're coming up with. So R is 0.005, okay? That is not the percent. The percent, move it 2 decimal places over, it is still a decimal, and it's a small one. It's 0.5%. This number is less than 1% decay. That's why I'm saying this number is not going to be too far away from 700. If I do less than 1% of 700, if I do 0.5% of 700, that's 3.5. And that's just for the first year, whatever. This number is going to stay around 680 something, right? It's going to be a very small decay. Maybe even 690 something. So let's see, W of 3. 700 times 0.995 to the third power. So, and that's kind of the expectation that I have when doing the problem, right? That's why it's good to have expectation. 689.55, so 689.6. 689.6. So it's very small change that you lose 0.5% of something over just the course of 3 times. You do it 1 billion times, it's gonna get closer to 0. That's understood. But just doing it 3 times over that time, very small change. Number 24. I guess these are the ones where we deal in decimal forms of percentages. So H of t equals 1250 times 0.865 to the t power. So A is 1250. You know, at this point, instead of thinking too conventionally, you can go more toward the calculator on these ones. So like here, if I do 1 minus 0.865, and I think that's 0.135, 0.865, oh, 0.865, I get, 0.135. So that is, and now times 100 is the percentage version of this R, right? So that's the decimal version. Here's the percentage, 13.5%. So we're taking away 13.5% of something, and you have 86.5% left. That's how that works. 13.5% decay. Let's do H of 3 and figure that out. I'm not going to try and estimate that one. I just know that it's, well, I don't know. Maybe if it's around 500 something, I believe it. Basically is all I want to say. Or more. Probably 700 something. Now I am trying to guess. I need to fill the air with just talking. That's just how I roll, guys. 0.865 to the third power. 800. 809.0. Definitely decay and not substantial. I mean, somewhat. Okay, 25 and 26 have an interesting bit because they are written as fractions, but we do need the percentage equivalence and all that. So, y is 7/8 to the t power. Now, I don't mind graphing. I kind of do for 7/8, but when I do graphs myself, I prefer fractions if I don't have a calculator to deal with. We have a calculator. Now, what I would prefer to do here in this situation is rewrite this in its decimal form. This thing's all about percentages. We have to work that. Furthermore, you could even talk about what A is. A is 1. We've mentioned this before. When it's missing, parentheses or not, when this thing's missing, that means it's a 1. 7/8, I know that's exactly 0.875. I know that fraction. I know the fractions of my eighths. So that's exactly 0.875, which is really close to 0.865, mind you. So the A value is 1 in this case, and the R value, if this was 0.135, this is 0.125, or 12.5%. So there's A, there's R. Let's find, this is Y again. Let's find it when we substitute T, 3 for T. I don't even need the 1. You could use the 0.875 or 7/8 at this point. It's up to you. If you want to use the original, go at it. 7/8 to the third power. Just make sure you use that in parentheses. I wouldn't have to put 0.875 in parentheses, but 7/8, the fraction, 2 different numbers in the expression, do have to be in parentheses for that. And they'll still give you the decimal. I wonder if there's a fraction version they'll give you. Yep, that. But here's the decimal equivalent. It's around they said nearest tenth, right? So 0.7. Around 0.7 is what we'll say there. So that's not very precise anymore, but it is still evaluating what it is that we're supposed to evaluate. Number 26, maybe more of the same. We have a fraction, a decimal with a fraction, never my preferred wombo combo. But the fraction, do we know what 3/4 is as a decimal? A is 0.5. You don't change that decimal equivalent to a percentage, are 3/4. That's 75%, y'all. I'm not even going to write the decimal version of it, but 0.75 is 75%. So we got that. Oh, excuse me. Oh, hold on a second. 75% is how much percent off? 25% off. Whoopsie. Maybe I should have written it to remind myself that that's what we're doing. It's not just 1 minus R is 75%, but R is 25%. Now, we are calculating with this in mind. 0.5 times 3/4 to the third power. Oh, I didn't move this over. Sorry. All right. 0.5 times 3/4 to the said power. 0.2109375. So 0.2. 0.2. Okay. All right. Let's do things that were kind of like the increases, only now, or growths, now they are decays. What represents the situation? Now they use the word decrease a lot. Get familiar with that. Decrease, decay, depreciate. Those are 3 different words that I would tend to see from these ones. I'm trying to think of other ones. For some reason, they're just not popping up for me. A population of 100,000 decreases by 2% each year. Now, 2% is 0.02 as a decimal. So the formula, all we're doing is writing the function. So this is 100,000 times 1 minus, it's a decrease, 0.02 to the t power. Don't leave it like that, please. Do simplify it. I request that for my students all the time. How many times they don't still make that change is ungodly unfortunate. I don't know, because when they get discredited, I'm like, guys, I not only stress it every time, I model it every time. If I model what I stress and I make no changes on that, do not fix that. And here's the thing. These are to the t power, right? We're just doing the model. The other thing I stress is always write the model first, simplified, and then substitute a number afterward. All right, a $900 system. That's our initial amount, 900 buckos. Decreases in value by 9% each year. Kind of like the other one, 0.09 in this case. So 100,000 times 1 minus 0.0. Oh, not 100,000. That's a great sound system, I'm sure. $900 times 1 minus 0.09 to the t power. 1 minus 0.09, take away 9% from 100%. That's 91%, 0.91. Simplified. And number 29, since this is our last one, I'll see if I can do this mentally. Maybe you can. A stock valued at $100 decreases, I don't know why I said increases, in value by 9.5% each year. The A is 100. The R is 0.095. Just because there's a trailing number doesn't make it, well, it is bigger, but it makes doesn't make it a whole digit bigger. So 100 times, let's see if we can do this. 91% is this. Subtract 99.5, that's 90.5%. So 0.905 to the t power. Maybe we can do that in one fell swoop. The idea is, though, guys, what you're not multiplying by a negative number. You're multiplying by a number less than 1 because you subtracted a number from 1. And that's what comes as a result of it. All right. Number 30 is error analysis. You purchase a car in 2010 for $25,000. The value of the car decreases by 14% each year. Describe and correct the error in finding the value of the car in 2015. I actually expected them to do a different error, and I'll say what I expected them to say here. But they have the wrong model. Let's just begin there. Their model is has 1.14 in it. They have the right 25,000. They have the right percentage change, but the change should be a decrease because this is a decrease by 14%. Their model should calculate 1 minus 0.14 instead of 1 plus 0.14. You should end up getting, well, I mean, here's the thing, right? Their amount of their final amount, and that's why I kept mentioning double checks, their final amount is more than the initial car amount because they increased it by 14% every year. It should be a lesser value, right? So that's part of it. Their double check. So our v of t actually should be 1 minus 0.14, which is 0.86. So v of t as an initial model, and always write that initial model if you can. So here, let me model this in full. 1 minus 0.14 to the t. Notice I'm still using v of t to begin with. 25,000 times 0.86 to the t. Okay, I wrote my model. Model. Always model a situation if you can, even if they mention years afterward. Just cut off that portion of it, make your model, then go from there. That's just a sturdy recommendation for all intents and purposes. That way you know what it means when they ask you about that. Now let's do v of 5, because they did the same thing. They just messed up. Now let's do v of 5. Now here's where I thought they were going to make a mistake. Why did we do 5? Because they're right with 5. Why did we do 5? The initial year was 2010. 2015 is 5 years later. The mistake I thought they were going to make was substitute 2015 in for their year. Now, that would make their value pretty much go to 0. Your calculator might even say 0. That is a lot. Yeah, that is... It'll probably say 0. It's a free car at that point, 2015 years later. Maybe not realistically so, but mathematically so, that would be the case. So, yes, 5 years later is what we're doing. And they go from there. So, yeah, I fully expected them to do that. So, let's see. Here's what I'm going to get. 25000 times 0.86 to the fifth power. Now, you can see that their number, they said about $48,000. That means they rounded to probably the nearest dollar. There will be a time, I'm sure, it's not yet apparently, and I'm going to write my number, 11760.67544. It's possible that later, when we refer to these kinds of things, guys, we will be doing dollars and cents. So I could say this many dollars and 68 cents or something like that. In this case, though, I'm going to say about, often I'm not going to say the word about, but 1176, if you round up, it's 1. So $11,761 for the car's value. Okay. Did they say some sort of round? Did they say round to the nearest 1,000? Because maybe that's what they did. It was more than just round to the nearest whole number. Purchase the car for them. Describe and correct the error. They've been doing the nearest 1,000 a couple times. If I round to the nearest 1,000, I would round up to 12,000. $12,000. So I don't know which one they're going to specifically want in this case. But that's me working that way. Yeah, I'm more particular. I often go to the cents. Because look, a car dealership is going to charge you 1 cent on the dollar as well. Look, if you pay 1 cent less than the amount, they're still going to give you the car. It's fine. You'll negotiate it down to that. But the point is, you can get to kind of that exact measure as well. All right, in 31 to 36, we'll determine whether the table represents an exponential growth, decay, or neither function explained. Now, the easy explanation is, oh, they do say neither. I didn't notice they said that before, because before in the examples I stated, all these will be exponential functions. That's actually not necessarily true. So I was going to say the easy way is, does it go up or does it go down as x increases? But because it can be neither, we'll make sure to refer to it. So my big thing, guys, is I'm going to come up with what that constant common ratio is. X is increasing by a constant 1, and it looks like, listen, I'm going to just look at them right now. X is always increasing by constant amounts. Adding 1, adding 1, adding 1, adding 1, adding 5, adding 2. X is increasing by constant amounts. We're good on that portion. We just got to figure out what y is doing over time. These y's are dividing by 5. They are each time. Now, I'm not going to say dividing by 5. That is not what we write in a ratio. We would say actually times 1/5. Y is multiplying by 1/5. Heck, its decimal equivalent is 0.2. Y is 20% of what it was. It's decreasing by 80%. We could say all that. But this is exponential decay because 1/5 is less than 1. So exponential decay. Y is multiplied by 1/5. As x increases by 1, y is multiplied by 1/5. So I can get as direct as that when mentioning those. And get ready for the next one. Number 32. Number 32 looks a little bit different. Just because the y's are going down doesn't make it decay, at least not exponential decay. If you look at this one, what's different on this problem here? X's are increasing by 1, sure. The y's are also decreasing by 4. Did I already copy the... Nope. That was the last text. Y's are decreasing by 4 in a linear fashion. That is a subtraction of 4. That is linear. That is not exponential. So x is increasing by 1. Great. But y is not times some number over and over. If it's a constant linear decrease like that, that is not exponential. So this is a neither case. So, okay, I guess neither cases will come up. Neither y changes at a constant difference of -4. As x changes by 1, right? As x increases by 1. Okay, number 33. Yeah, these are ones I can kind of do a little more quickly if I wanted to. I mean, I kind of want to. But if I wasn't writing every part of the answer. So, as long as I involve everything with you, I'm going to write as much as I feel I need to. Y, again, looks to be having... And these are all decay for some reason. When are we going to start increasing? But for here, y is another going down by a certain amount. But as you can tell, it's a subtraction of 6. Kind of same issue as before. This is linear. This is not exponential. So if I kind of take what I stated the last time and do it again, y changes by a constant difference of -6 as x increases by 1. That's linear. That's not exponential growth or decay. Number 34, y is increasing this time as x increases. It's some form of growth, but is it exponential growth? That's the question at hand. We got to figure out what we're potentially multiplying by each time. It doesn't look linear to me. It looks like it's going pretty large pretty fast. So there's a great chance it's exponential. We'd have to work on that, though. 17 times what is 51? If you don't know what it is, you do 51 over 17 to figure it out. Now, I know what it is. That's 3. So we are multiplying by 3 going from this number to the next. The question is, as x increases by a constant 1, is this times 3 153? I'd say yeah. And this one here, I'd also say, yeah. I don't think it's a trick. Like, they go like, ha, it was actually 458, you idiot. Like, what's wrong with you? You should have really checked it. No, that one's increasing constantly. This is increasing by a constant multiple, constant ratio. So, yes, this is exponential, but it's exponential growth. Exponential growth. As x increases by 1, y is multiplied by 3. Okay, number 35. This just has a lot of inner workings. I have to copy and paste the table. I got to change the things. I got to type some things out, all that kind of stuff. Now, x is increasing by a constant amount. It doesn't matter that it's not by ones as long as it's a constant increase of adding the same thing over and over. This still works out that way. That doesn't, therefore, mean that y's percentage change as x increases by 1 is what you think it is. In other words, we are adding 5. Sure, that's fine. That's all good. And y does appear to be multiplying by 4, so this is exponential growth. That doesn't mean that as x increases by 1, y multiplies by 4, right? But it does mean it's exponential growth. Okay. And then number 36, x also increases by a constant amount. We established that, increasing by 2. Now y is making some changes. Some shrinkage, substantial shrinkage, and less shrinkage over time. Kind of looks like exponential decay, but if it is, then we got to figure out what it's multiplying by, right? So this is one of the things. 432 divided by what is 72? You might say, oh, gee, I don't know. Now, you could do 732 over 432 to figure it out, but those are still massive numbers. Even I might be at pause for that. So what I'd rather do is look to the smaller numbers wherever I can. 12 and 2. 12 divided by 6 is 2. I think we all know that. So there you go. Now, we want to say what we're multiplying by. If we're dividing by 6, then we're multiplying by 1/6 times 1/6. Now, are we doing that here? Are we timesing 1/6? Well, divided by 6 there, yes. And you can double check this one. I'm going to go ahead and say that, yes, that's true. So these ones here are all times 1/6. So it does make it exponential decay, despite the fact that x is increasing by 2. That still works out that way. So I'm going to say here, exponential decay. As x increases by 2, y is multiplied by 1/6. Probably was faster to type, but that's okay. All right, those are those 6. Let's move forward. Analyzing relationships, number 37. The table shows the value of a camper t years after it is purchased. Determine whether the table represents an exponential growth function, an exponential decay function, or neither. That's part A. Part B, what is the value of the camper after 5 years? So even if it's not exponential growth or decay, apparently we still have to come up with the model. So I'm going to copy and paste that table. Let's do some comparisons here. These are something where I have none chance in figuring out what we're dividing by, whatever. But technically, we've got to figure out what we're multiplying by, right? As far as the whole formula goes, in this 1 minus r fashion, we got to check and see if we're multiplying by the same thing from one value to the next. Times r? Is it times some r here? I got to figure out what 29,600 over 37,000 equals. I got to see if it's the same as 23,680 over 29,600. Honestly, if these two are the same at that point, I'm going to assume it is decay at that point. I'm going to assume the last one is doing the same thing. Even if it's roundabout, they might be rounding our numbers. I have no idea if they are or not. But if it's not the same after the first two, then I also know it's not exponential, which is likely going to mean it's linear. So let's do a check on these two just straight up. Let's do 29.6. Remember, it's one number divided by the one before it. 29.6 divided by 37. Thou. That's 0.8. So exactly 0.8, which is cool. I didn't know what to expect on that one. Now, you can do one of two things here. You can either do one number divided by the one before on the next one, see if I get 0.8, or I can try and multiply these numbers by 0.8 and see if I get the same result. So actually, let me try that test. That's actually a little fancier for me. Let's see. We're multiplying this by 0.8. Are we doing times 0.8 here? Let's actually do 0.8 times, oh no, I cleared all of that out. That's okay, I don't need it. 29.6 times 0.8. Do we get 23,680? Yes, we do. And times 0.8, do we get 18,944? Yes, we do. Okay, so this is the same as the others. This is 0.8, 0.8, 0.8. This does make it an exponential function. Specifically, 0.8 is less than 1. This is exponential decay. So this is exponential decay. Now, I did a lot of work in getting there. I kind of erased some of it. I apologize. Let me actually write that one part out. Actually, let's just do this whole thing. This divided by this equals this divided by this equals this. And these are exact. These weren't even rounded, which was kind of one of my fears, saying, it's close enough. These are exactly 0.8. It's exponential. Okay, now they said determine whether it is one, the other, etc. So we found out exponential decay. Part B, what is the value of the camper after 5 years? For us to do this, here's the tricky part about it. Well, okay. You have two options. Option one, they say T years after its purchase. Option one is write your function with 37,000 as your initial value. The tricky part about this is that's year one, not year zero. So if I do 0.8 raised to a power here for a model, this is currently first year, after first year. 5 years later, 5 years here, look, I could multiply this by 0.8 and I'll be good as well. I don't know if they want us to write the model or just multiply this number by 0.8. We should get the same answer. But the point is, I got to substitute not 5 for t. I got to substitute 4 for t because I'm starting at the first year. 5 is 4 years later. And I believe this chapter hits geometric sequences. You're going to be looking at this same kind of thing quite often there. So this is an option on what to do. And if I go to the calculator, I'm going to get 37,000 times 0.8 raised to the fourth power. This number will be that guy. Now that's money. So I'm going to put cents on this one this time, just whatever. I'll do, just to hit a point, $15,155.20 is what I'm writing for that. Okay. So that's what it is in the 5th year. This is part B, by the way. That being said, we could do that. The second easy option is take this number times 0.8, like literally. I could just do that value times 0.8. So if I go to here, because that's the 5th year, right? The 4th year was there. And if I do 18944 times 0.8, I should get that same answer as this one. Now the third option is a little bit trickier, and I don't know if it's worth its weight in gold or not. The 5th one is to find out what year 0 would have been. You divide by 0.8 to go this way. You figure out what year zero's amount was when t is 0 like that. You use that in the calculator and then make that for your equation so you can substitute 5 for t after. The reason why it might not be worth its weight is twofold. Number one, how crazy is the number? It's actually not crazy at all. It's still a whole number. So 46250. Number two, it might take more time than you actually need for it. So if I take this one here, I could write my model as y equals 46250 times 0.8 to the t power. This is the 0th year. This is initial amount or whatever. That way, 5 years later, you actually substitute 5 into there. And 46250 times 0.8 to the 5th power gives you what they give you. I'm willing to bet that's not what they wanted you to do for the situation. It's kind of your call. Listen, you're going to get that number. Try it in your calculator if you like. It's really your call, but since they didn't lecture you on that, probably not. I'm guessing it's more of what we did right here because they did lecture you on something like that before. But it's also just 1 year away from year 4. So once you find your number, just do another times 0.8. It's just as convenient. They didn't force a method on you. They just said, what's the value of the camper after this many years? So for me, about that. And now that was to cents. They could do to dollars. They could do to $1,000, around 15,000. I'm going to cents just to show you what you do. 2 decimal places, even if only one sticks out in the answer. All right, number 38. The table shows the total number of visitors to a website T days after it is online. This pushes more to what I was saying before, that this is, they start at 42 here. They're not starting at 0. They're not starting at 1. This is quite later. So this is you picking and choosing what you want to do, I think. Determine whether the table represents an exponential growth function, a decay function, or neither. Well, it doesn't look linear. I'm going to say that. So I'm hoping it's still one of those functions. In this case, probably a growth function. Because if it's not, and it's not linear, then I don't know what to tell you. I won't be able to figure out that answer in a very easy way. So here, we got to check what, I'm going to do this in the calculator, but 12,100 divided by 11,000 is. So 12,100 divided by 11,000. I'm going to compare that number, 1.1, to 13,310 divided by 12,100. Is it the same? Yes, it is. And 14,641 divided by the... If I thought about this quickly, well enough and saw these numbers, I actually would have known that, because this is, it's kind of hard to explain, but this is 11, this is, without the zeros, that's 11 to the first power, 121 is 11 squared, 1331 is 11 cubed, right there, right there, right there, and 14641 is 11 to the fourth. I actually know those numbers based off something called Pascal's triangle. So I probably could have figured out that that was some form of 1.1, but I didn't. Anyway, so yeah, this is times 1.1 each time. Like that. So it is exponential. It's exponential growth. Now, this model, once again, it depends on if we want to play with the model or what have you. We have to express this as an initial amount, but that's at year 42. They say, or for day 42. They say part B, how many people will have visited the website after it is online? 47 days. T days after it's online. This is 42 days. 47 is only 2 days away from 45. So you have 2 options. Write a whole function. This time, let's just do the recursion portion of this. 47 days. Let's do 14641 times 1.1 times another 1.1. That's also times 1.1 squared, if you know. So that's one thing you can do for this one. So for 47 days. And there, we're going to hit decimal land here. 17715.61. Now, as far as this goes, this is people. So we want to, what did they say, a rounding thing? They didn't, but we want to round. 17716. It's people. Visitors. After 47 days. Again, if you make a model, you can make this the initial, but 47 is 5 days after this, so you would do this times 1.1 to the 5th power. Notice I did 1.1 squared because that's 2 days after 45, right? It's the number of times you multiply by your number. I'm not going to go all the way back to day 0, basically. I don't know what day 0 would be in that way. That's why I don't think it's going to be that one that I was mentioning before, how we wrote it. Sorry, you probably didn't see me write this. And, yeah, just want to make sure you're aware. All right, 39 to 46. They say determine whether each function represents exponential growth or decay and identify the percentage rate of change. Doesn't sound much different from what we were doing earlier, only this time it meshes growth with decay. So we have to make our determinations each time. Is the number inside more than 1 or less than 1? That's basically the thing. So we don't have to explain it, just determine it. So number 39 says y equals 4 times 0.8 to the t power. 0.8 is less than 1, therefore this is exponential decay. So given that it's exponential decay, the R value, it says identify the percent rate of change. It's still the same thing. You know, this is, I'll do it for this problem. 1 minus R is 0.8. You subtract 0.8 there. R is going to be 0.2, but the percentage is 20%. 20% decay, really, right? That's what we're talking about. Once we identify decay, we say 20%. They know what we're talking about. How much from 100% is your number? That is always the question. Whether growth or decay, that is always the question. So you can also interpret it that way if you know what the percentage equivalent of the first number is. Keep in mind, I don't care what this initial value is. We care about what this number is here. 1.1 is more than 1. This is exponential growth. 1.1 is also 110%. 110% is 10% more than 100%. So R is 10% of change. Of course, that's also 0.1 as a decimal, right? There's so many ways you can talk about when you want to convert from decimal to percentage. Do you want to do the subtraction? Things like that. Let's say that one more time on this one at least. See if it sounds right. If so, I'll carry on that message. Y is 30 times 0.95 to the t power. 0.95 is a number less than 1. That's 95% of something. So given that it's exponential decay, the question is how away is 95? How far away is 95% from 100%? It's 5% away. So your R is 5%. 5% decay to make it 95%. Make sense? Number 42. Yeah, I think at this point, because we've done these before, it's just that now we're, like I said, meshing them together. At this point, I think I have the right to be able to go faster with them now that we know what these numbers mean. 1.08, this time we'll say them as far as decimals first and convert them after. This is growth. It's more than 1. That makes an R value of 0.08, which is 8%. So notice that time that I did the difference of 1.08 and 1 to say the decimal first, which is what we have to do in our formula, and then we convert to a percentage afterward. That's a your call thing. Still get the same answer, no change. Number 43, function notation will still not change what we're doing, and having an A value that's a decimal still is no change in what we're doing. R of t is 0.4 times 1.06 to the t power. Fact of the matter is 1.06 is more than 1. That makes this growth. And it's growth by 6%. The other was 8%. This is 6%. Very straightforward. Very straightforward. Now 44, again, despite the fact that we have function notation, or despite the fact that A is a number less than 1, that doesn't matter. But R seems to be subtracted this time because our thing we're multiplying by is less than 1. That'll make this exponential decay. How much exponential decay, you ask? Well, we can do 1 minus 0.48 to figure that one out, and that would be 0.52. 0.52 is also 52%. So this is 52% decay. We were losing more than half of your amount, and you already have a small amount to begin with. Oh my goodness. Good thing this isn't a real-life application. All right, 45. 45, not going to call it tricky. In fact, we've done things with fractions before, but there's one more wrinkle to this fraction than before. Anytime people see fractions, they might think decay. If it's a fraction, it's decay. No, if it's a fraction less than 1, it's decay. 5/4 is an improper fraction. 5 divided by 4 is more than 1. In fact, we might want to write what 5 divided by 4 is because we got to come up with that percentage version. It's 1.25. It's like 5/4, right? Literally, 5/4 is $1.25. That's what it is. This is exponential growth because it's a number more than 1. You're adding 25% to 100%, so it's a 25% growth. And then number 46 is 4/5. Well, that's not an improper fraction. That is very proper. It's one that is less than 1, therefore it will be decay, but I don't think that it changes how we might want to convert it to decimal form before converting to its percentage. Now, A is 1. That doesn't really matter to us, but it does matter that it's decay. In fact, let's write that thing. 4/5 is 0.8. So 0.8 to the t power. Keep in mind that is your B value. 1 minus 0.8 is 0.2. 0.2 is 20%. That's our R value, 20% decay. Take 4/5 of something, you're taking 1/5 off of something. You're taking 20% away. Those were quick. Now we're going to problem, 58? So home stretch, 12 more questions. This is where we start hitting our interest problems. Numbers 47 to 50 says, write a function that represents the balance after t years. Now, before I start up the problems themselves, let me also make mention that we're using this formula here, a equals p times 1 plus r over n to the nt power. It's very similar to what we had before, only we're always adding for interest. And n is introduced. Oh, we changed the... Actually, they used y, so I'm going to use y here. Although, if you see a in a formula, if you ever see me write that again, apologies, it's habitual. It doesn't change what we're finding, a final amount. N is introduced here. This is how many times you compound over years. The other thing is... Oh, we're just doing the model. But the other thing is, guys, t here is always represented in years. It's never months or anything like that. So if they give you months, you got to convert it to years. All right, so 47. We have a $2,000 deposit. That's our principal amount. 5% annual interest is R. 0.05 is a decimal. It says compounded quarterly. That's an N value of 4. So initially, we're going to write out y equals 2,000 times 1 plus 0.05 over 4 raised to the 4t power. If you can simplify, please do so. And I say if you can, meaning sometimes these don't divide very well. Sometimes it becomes a, if it was 0.05 over 3, now it's a repeated decimal. Maybe you'll leave it like that. 0.05 over 4, I believe, is 0.0125. 0.0125. So 1 plus 0.0125 is 1.0125, like that. So I'm going to write it like that instead. This is to the 4t power still. Keep in mind, whatever's up there, if we said after 10 years, we'd plug in 10 for t and we'd multiply it by 4. We get 40 because it would compound itself 40 times over the course of those 10 years. It does it 4 times a year. And that's what we get for that one. Number 47. Number 48. We have a $1,400 deposit that earns 10% annual interest compounded semi-annually. Semi-annually is twice a year. So principal is $1,400. R is 10%. That's 0.1 as a decimal. N is 2, twice a year. So this equation will say 1,400 times 1 plus, it's always a plus, 0.1 over 2. You should know what half of 0.1 is, to the 2t power, without a calculator, please. Half of 2 is 0.05. I was about to say 0.5. And 0.05 plus 1, is 1.05. So 1.05 to the 2t power. There's our model. Of course, we'll answer questions for those pretty soon, I'm sure. Number 49, $6,200 deposit that earns 8.4% annual interest compounded monthly. Okay, I think at this point, we're pretty well aware of what we're substituting where. Initial, percentage change, and compounding. Compounded monthly, your N is 12 times a year. So let's see if we can work this one out. Y equals 6,200 times 1 plus 0.084 over 12 raised to the 12t power. Now I'm going to try and simplify this. I believe it should work because 84 divided by 12 is 7. So 0.084 divided by 12 should be 0.007. I'm going straight into that. So y is going to be 6,200 times 1.007 raised to the 12t power. So they're giving us numbers that I think clean up each time, and it's best that they do so we can keep emphasizing the fact that we should simplify it when we can. As long as we can, we should. We're back to compounded quarterly. That's no change for us. Hopefully you're good on writing those decimals now like these ones because the next one shows up this way. $3,500 deposit is our principal. My neck, man. This isn't going to change for some future videos here in this chapter. Times 1 plus 0.092 quarterly is over 4 to the 4t power. 0.092 over 4, 92 over 4, 23, so 0.023. So y is 3,500 times 1.023 to the 4t power. Okay. Cool. Now we're going to use those ideas for some of the future problems we have. We have 8 more problems to go, I believe, in the section. Probably a lot of interest or how do you see it, making arguments, things like that. Problem solving. You have a checking account and a savings account at a credit union. The table shows the total... your checking account has a constant balance of $500. The table shows the total balance of the accounts over time. So keep in mind, we're adding $500 to what we have in this case here. We saw an example of this before. So what I'm going to do is copy and paste this table, and I'm going to write what these numbers look like if the 500s are not involved, because they say write a function m that represents the balance after t years. This is total balance, which is adding your cost amount, your checking account amount. So your savings account, your savings balance will be 500 less than any of these numbers here, which is the ones we need for our other function of the savings account. So this is 2,000. This is 2,040. 2080.80. 2122.42. 2164.86 and 2208.16. This is important because the percentage change is dependent on this. Times what, times what, times what. And it's going to be the same thing each time. They already say, well, they don't say, but they said write a function. It's going to be exponential. So I really just have to check one of these. Let's do 2040 divided by 2000. And that'll be 1.02. So this is times 1.02. If you want me to double check here, I'm going to also do the next one times 1.02. That times 2040. Do I get $2,080.80? Yes, I do. So that is the number set that's going there. So for us, when it comes to writing a function m, we won't say y equals this time. We'll do m of t. M of t equals, our year 0 is our principal investment. In this case here, this is for savings, by the way. We're going to take 2,000 times, and this is annually, by the way. This is here. So our n is 1. We're not compounding it more than once a year. So 1.02 is our multiplier, by the way, raised to the t power. Here's our m of t part. It's part A. Part B says write a function b that represents the total balance after t years. Compare the graph of m to the graph of b. This one, we're going to add 500 to these numbers each time. So b of t takes your m of t and adds 500. Or b, I guess for balance, is 2,000 times 1.02 to the t power plus 500. It's like ab to the x plus k, right? So there's that. We can graph these, and I'm going to use a graphing calculator for it. So, kind of bring this up first so you see what we're going to take a snapshot of. I'm going to take this equation and this equation as my two things to graph. So we're going to go 2,000 times 1.02 to the t, we have to say to the x, and then 2,000 times 1.02 to the x plus 500. I'm going to make this a thicker line on this one so you know that that one's different. Whoops. I can't go over there. There we go. It'll be the higher up one. Now my window range, I need to show some higher up numbers. I don't care about those x's. We're going from 0 to 5, it looks like. And then y's, we can start at 2,500 and kind of go, I'll do 2,400. But we'll go up from there. No, excuse me, it's 2,000. Let's start at like 1,900. And then let's go up to about 3,000 just to kind of get a good snapshot of them. So these two graphs, here's our first curve. And it is a curve. It might look like a line just because of our window range thing, but it is curving upward, make no mistake. If you want me to show you more of a curve, actually, let's zoom this out a little bit. Let's go from 0 to 10, and maybe it'll give you more of the curve. Here's the thing. We're only increasing. Oh, I need higher y values now, though. Hold on. I don't know how high. Let's go to 4,000. Maybe that's not enough even still. But maybe it'll show a little bit more of a curve because we zoom out more, or maybe not. To you, you're like, it's still a line, Mr. Robinson. Remember, there's only a 2% change each year. So at some point, I would probably have to do a lot more zooming out to show you what it is. I want to prove it to you that it's a curve. You should know this is an exponential function, but let's just zoom it out a little bit more, and then I'll bring it back. Let's go to 20. Let's see more of that curve. Maybe it's not going to give us enough of a curve to show it. I don't know. I'd have to zoom out quite a bit to actually accentuate the curve. I don't think it's worth doing here for the sake of what we're talking about. It's okay. You can probably see a slight curve there, right? But it's just not much of a change. 2% increase every year is just not much of a change. Anyway, very slight curve. Let's go back to what we were talking about from 5 here up to about 3,000. Let's take a snapshot of this. Sorry that I wasted our time talking about lines versus curves. But this is where you get to play with window ranges, see what you want to see from it, and we're comparing one to the other here. They said compare the graph of M to the graph of B. Literally, one is just 500 higher than the other at any one given point. No, I don't have the exact points written on here or anything like that, but that is the comparison. So here, the graph of B is a vertical translation of the graph of M by 500. It's 500 bigger everywhere. At any year, you have 500 more in your total balance than you do in your savings. Part C, compare the savings account to the account represented in exercise 47. I don't know, it was 47 the last problem? No, we're on 51. $2,000 deposit that earns 5% annual interest compounded quarterly. So compare the savings account. So the savings account is this guy. So 2,000 times 1.02 to the t versus 2,000 times 1.0125 to the 4t. All right, compare this guy. Give me a second. Come on. All right, number 47. And I guess it should be y equals. Did I not write y equals for this? All right, number 47 and then number 51a. So 51a was 2,000 times 1.02. All right, it's one of those things where, 1.02 is actually more than this number. Just because it has more numbers doesn't mean it's a larger number. Because this is a 1.25% change, but it's 4 times in the year thing. That's what makes this questionable as to which one's the bigger number. Let me go to the calculator again, and let's compare. Let's get rid of the bottom one. Let's check out how this one works. I don't think it's going to be larger, but it's not as small as you think in comparison. And maybe we actually have to do this comparison. Here's one and here's the other. I might have to change the look of the scale. So it's underneath. Okay, yeah, it lessens over time. It's a little less over time. So it's less than when it comes to this stuff here. Not by a significant amount though, right? So each account has an initial balance of $2,000. That's one part. Each account has an initial balance of 2,000, excuse me. And then one of them has the savings account that is earning 2% interest per year. The savings account. While the other account earns... Oh, you know what I didn't do? Hold on a second. I didn't do to the 4x power. I just said to the x power. That's why. I thought I said I thought it was going to do more. Let's see this again. I was surprised when it went under. There it is. Now, why is that getting more? Why is that getting more? Because the thing is, it's compounding the interest from something that was not 1.25% before. It's doing 1.25% 4 times in the year. That's 5%, right? So while the other is earning 5% interest compounded quarterly. So the number 47 interest or account, was it an account? Increases faster. Okay. All right, let's move forward. Some of these things have trouble like processing and saying right. Combining functions, number 52. You deposit $9,000 in a savings account that earns 3.6% annual interest, compounded monthly. You also save $40 per month in a safe at home. Write a function, C of t equals B of t plus H of t, where B of t represents balance of your savings account, H of t represents amount of your savings account after t years. Okay. Find and interpret C of 5. So we have a few things going on. We have B of t is the balance of our savings account. So B of t is going to be 9,000 deposited times 1 plus 0.036. This is compounded monthly over 12 to the 12t power. Remember, t is represented in years. Okay. T is in years. H of t is home. H of t, now t is still in years. This is the tricky part. It says you save $40 per month in a safe at home. The interesting part about that is 40t won't do it. 40 is per month. T is the number of years. If you want to do the number of months here, you should also do times 12t in its own way. This is the same reason why we do this in this kind of way at the 12t here, because this is done every month to this percentage. The one that you splice up that many times. This is 480t. So our combined function will be C of t equals, this is on a yearly basis still, this thing, and by the way, I don't know, let's see, 0.036 over 12 simplifies to 0.003, so this will be 9,000 times 1.003 to the 12t plus 480t on that guy. That's how much we save on a yearly basis. It says find and interpret C of 5. So we're going to find C of 5 by doing a substitution of this. I'll go to the calculator for it. To interpret it is straightforward. How much money we've saved after 5 years. T is still in years, and we represented these in years by doing what we did here. Especially in the home savings portion. God, it's getting seizure back here from Olympics montage or whatever that is. Now, here's where I got to be careful. I got to use parentheses here when I do 12 times 5. Of course, 12 times 5 is also 60. When in doubt, do some calculations that you already know how to do. So plus 480 times 5. Remember, the 480 times 5 is how much you're doing for the 5 years at home. So $13,172.05. If you want to do the 5 cents, I'll go ahead and do that. So 13,172.05. Okay. This is the amount of money saved in total. Let's see, combined in savings account and at home after 5 years. Okay. Number 53 on number sense. During a flu epidemic, the number of sick people triples every week. What is the growth rate as a percent? Explain your reasoning. I actually mentioned one of these in a previous problem with the 200%. So 53, see, this is a percent growth. This is 1 plus R is 3. It's tripling, 1 plus R. Therefore, R is 2. That's 200% growth. I explained it through mathematics, basically, right? It's not 300%. This is a tricky one. It's not 300%. It's an increase from 100% of how much? It's a 200% increase from 100%, which is where we get that number. Number 54, how do you see it? Match each situation with its graph. Explain your reasoning. So, I hate when they have us explain. Part A, a bacterial population doubles each hour. I'm just going to be writing the letter in the reasoning. So if it doubles each hour, it can't be B or C. Those are decays. This goes from... Yeah, I can't tell. Let's see. These scales are kind of hard to go off of. This is 4, this is 8, etc. So that's probably not the doubling effect. That was a little low. This one here starts at, I think, 50. After 2 hours... It's 100. After, wait, I don't know if that's 100 yet. This, I think it's D. It's hard to see on this one just because the scaling is just bad. Let's figure out when it actually hits. Okay, how about this one? When, all right, it's not A. It's not increasing quite enough here. This one has to be D. This one has to be D because the rate of increase. Rapid rate of increase. I can't really see the exact numbers that it goes by because the scaling is so, like, diminished. Now, I can't even guarantee that's 50. I just said it's like 50, but I don't know. So, yeah, that seems to be a nice rapid rate on that one. Part B, that's how I see it. The value of a computer decreases by 18% each year. Okay, actually here, before we do that one, let's look at the other ones. Deposit earns 11% annual interest. Yeah, that's going to be a slow increase there. Radioactive element decays 5.5% each year. We have to compare the 18 to 5.5. Which one lessens less? This one lessens less. It has a smaller decay than this one. Therefore, it's not going to be as strong of a thing. And all the scales are the same. This goes 8 and 16, etc. So C lessens less, B lessens more. So part B is graph B, decay at moderate amount, at moderate rate. Compared to that at least of D, but part C is the deposit earns 11% annual interest compounded yearly. That's going to be A, graph A. That is a lesser rapid rate of increase. Lesser rate of increase. Compared to that of graph D. And then part D gets graph C. That's a lesser rate of decay compared to graph B. C. So that's me comparing things right there. You know, I'm not actually taking numbers and calculating it. When they say, how do you see it? I think we should do more on the graph, less on the calculations. Number 55 on writing, give an example of an equation in the form y equals ab to the x that does not represent an exponential growth function or an exponential decay function. Explain your reasoning. I'm guessing if you make something negative, let me think about it. If you make, it's all about b value. If I make the b value negative, or if I make a 0, y equals ab to the x. Let's do y equals 2 times 1 to the x power. Multiplying something by 1 doesn't make it grow or increase or decrease. B cannot be 1. B cannot be 1 because it will neither increase nor decrease. Making it constant instead of exponential. Y will always be 2. No matter what I substitute for x, 2 times 1, because that's all, it's just going to be a 1, will always be 2. So it's making it constant instead of exponential. It's not even linear. I guess it is, but it's also constant. 3 more questions. Number 56. How long have we gone? I'm always curious on those. Yikes. Describe 2 account options in which you can deposit $1,000 and earn compound interest. Write a function that represents the balance of each account after t years. Which account would you rather use? Explain your reasoning. Now, if we're talking about the same percent, I don't know. Let's do a compounded annually and let's do a compounded quarterly. At least that way, if I divide by 4, then I know I'm going to get something there. I could do like compounded daily and divide by 365. Those are good ones. So let's do something like deposit $1,000. I said 1,000, right? Earning, let's say 5% interest. Let's see. I want to make clean numbers. What can divide by 4? 4 and 8. Earning 4% interest compounded annually. I guess this one I'm not dividing by 4, huh? So there's going to be one here, and then we'll do earning 8% interest compounded quarterly. Actually, let's do 4% for both of them. So you can see what the change is on this. Okay. So 4% interest compounded annually, compounded quarterly. Says after t years, which account would you rather use? But we might have to plug in some numbers and see how they actually look in comparison. So this one is y equals 1,000 times 1.04 raised to the t power. Straight up. And this is y equals 1,000 times 1 plus 0.04 over 4 to the 4t power. So that's 1,000 times 1 plus, 0.01 or 1.01 to the 4t power. Now, the interesting part here is you look at these and you might say, oh, I like this one more because 4 is more than 1. Yeah, but this one has a 4 here. You're like, oh, so they're the same. Not quite the same. quarterly is slightly bigger than, and I say slightly, it's slightly bigger than the other one, especially at 1%. It's not going to be much of a change. So if I compare these two, I'm not even going to look at their graphs. I'm going to look at their tables. But 1,000 times 1.04 to the t power, and then 1,000 times 1.01 to the 4. This is the part I forgot last time, to the 4t power. Let's go to the table and let's look at years with that. Look how y2 is going to be slightly bigger than y1 as we increase the number of years. 10 years later, this says about $8 more than this one. You go, ooh, $8. The point is it's more. It's more when you compound quarterly. Imagine compounding monthly and all that. Now there's diminishing returns on it. You don't get significantly more over time. But just compare after 25 years, whatever. Now it's, $40. Ooh, right? But, deposit more, get a higher rate of, change and increase, something like that. You'll see more. But anyway, I prefer more money than less money. So compounded quarterly is preferred. All things being equal. All other things being equal. Compounding more generates more money. More interest. Therefore, I would prefer the option. All right. There we go. Okay, number 57. Making an argument. A store is having a sale on sweaters. On the first day, the price of the sweaters are reduced by 20%. The prices will be reduced by another 20% each day until the sweaters are sold. Your friend says the sweaters will be free on the 5th day. Is your friend correct? Explain. No. My friend is not correct as usual. My friend is not correct. Decreasing a price by 20% every day is not a subtraction of 20% of the original amount every day, but rather of the previous value. Now, if you want to know what it is, remember what we're doing, and who cares what the initial amount is? I just care about what we're multiplying by as an overall. 20% is decreases 1 minus 0.2. When you raise that to the 5th power, that's 0.8 to the 5th power. Now 0.8 to the 5th power is what we're going to multiply by here. Let's see, 0.8 to the 5th power. That is 0.32768. Now 1 minus that is what we're doing for our change there. So it's a lot that we're saying here, but 1 minus, well, okay. You can either say this as 32% of price. Okay, I'll actually say this. 32.8% of, I'll say 33. It's about 33% of the price. Or about 67% off that price, right? It's not free. 33% of the price, though, is pretty good. 67% off, still pretty good. If it was a $100 sweater to begin with, now it's $33. It's not free, but it's 33. All right, number 58, last question. Comparing functions. The graph of f and g are shown. Hey, back to graphs. K times f of t, where f of t is 2 to the t. Explain why f is an exponential growth function. Identify the rate of growth for 58 part A. So let's do this. Let's pull that graph over here. Come here. All right, f of t, 2 to the t power. Well, first of all, I don't know if I need the graph itself to answer the question. It says right there the rate of growth. F is exponential growth because the b value, 2, is more than 1. I mean, whether we're seeing it as a 1 plus r or whatever you want to say, f is an exponential growth function because it grows. Because I'll say 1 plus r is more than 1. Because b is more than 1. We're making it a 1 plus r equation. It says identify the rate of growth. The rate of growth is that 1 plus r equals 2. 1 plus r equals 2, therefore r equals 1, which is 100% growth. It's doubling. It's doubling. That's what 100% growth looks like. Part B, describe the transformation from the graph of f to the graph of g, determine the value of k. So I think we're not supposed to say it in terms of k. We're supposed to say that it's, we're supposed to figure out the number, right? So here, we need to figure out, first of all, it's a vertical stretch, what it multiplies by there. The initial y-intercept was 1, now it's 4. It makes it 4 times bigger, that kind of thing. So G is a vertical stretch of f by a factor of 4. That is the actual stretch itself. Part C, the graph of G is the same as the graph of h of t equals f of t plus r. Find the value of r. Explain your procedure. So we're now talking about a horizontal translation for this. So if h of t equals f of t plus r, you have to remember t is our variable here, like our x. R is how much we're translating. You can see here, as far as translations go horizontally, take this point right here and find another one of the same height. It's over here. We have to go 2 to the left for that. Therefore, the r value going 2 to the left means r is 2. So r equals 2 means h of t equals f of t plus 2. That's where we're shifting to the left. Explain your procedure. This represents a horizontal translation. And f of 0 is the same as h of negative 2 because they're both 1. Therefore, you would have to add 2. Let's see. Is that right saying it that way? ft plus 2? Yeah, therefore, you would have to add 2 to a value to make it the same height as the one before that. So translating to the left makes a plus appear in the function because it's opposite, etc., etc., etc. So it should be that. R is 2. And that's the last one. I know that that's more of a transformation question, less of what we said before, but we did talk about the 100%, so that's still good. Guys, that'll do it for this one. This is Mr. Robinson. Thank you so... What is happening back here? Thank you so much for watching this one here. We still have one more section before, and I forget what the section is, but one more section before we hit, I think it's exponential and linear model comparison, before we hit our 6.1 to 6.3 quiz. So check out that recording in a bit. Thank you so much. Take care. I'll see you in the next one.